Hi, my name's Thomas Sears. I'm a PhD candidate at Queen's University in Kingston, Ontario, Canada. In this presentation, I'm going to be discussing research that I completed with my supervisor, Dr. Joshua Marshall, where we looked at a technique for modeling changing natural environments with in situ mobile robots. This research is more thoroughly discussed in our paper titled Mapping of Spatiotemporal Scalar Fields by Mobile Robots Using Gaussian Process Regression. We undertook this work as a first step toward improved control performance for robots operating in dynamic environments. As illustrated in the control block diagram, typically environmental disturbances are either unmodeled or use a static model. We would like to replace this with a time-varying model generated in real time from onboard observations. Now, such a strategy would benefit any vehicle affected by structured or repeating forces, but our focus is eventually to use these techniques for an uncrewed surface vessel encountering surface waves. To begin, we needed to identify a feasible means to recreate a space and time varying phenomenon, which we refer to as a spatiotemporal phenomenon, from the measurements made from a single mobile robot. Now, many previous studies have addressed modeling spatiotemporal fields, but most have used arrays of static sensors. And when mobile robots have been used, the phenomenon under investigation is typically static itself. In our research, we aim to merge these two fields of work in order to create a mobile sensing and spatiotemporal mapping solution. It's also worth noting that such an outcome benefits more than just robot control. Where static sensors are typically used for environmental surveys, a mobile robot could now instead be used. This would provide lower cost, faster deployment, flexibility, and new opportunities previously unavailable to researchers with traditional sensing methods. We consider the challenge of a mobile robot mapping a spatiotemporal scalar field. The difficulty in this scenario arises from a lack of observations. Our vehicle can only be in one place at one time, and although we can revisit physical locations, the robot cannot revisit times. This is shown in this illustration of a vehicle moving from red to green to purple as time progresses. We want to estimate the field at the locations and times never visited, indicated by the arrows. As we desire to make minimal assumptions about the structure of the spatiotemporal field, we instead rely on similarities in the data to build a spatiotemporal map. This leads us to using Gaussian process regression, where data-driven models are created through correlations in the data. With input location and time data and measured scalar field values, shown in gold, correlations are calculated with the kernel functions that we select prior to the modeling. After optimization, the output is a spatiotemporal map. We select two kernel functions to quantify data correlations, a squared exponential kernel and a periodic kernel. The squared exponential kernel is largest for values closest to the test point, whether that be in space or time. A length scale hyperparameter determines the decay rate of this correlation function. Periodic kernels are largest when the distance between two inputs is equal to a multiple of the period, p. A length scale hyperparameter in this case determines how broad the peak of the correlation will be. Now, as a means to limit overfitting of the model, we consider hyperparameter constraints based on vehicle speed, v, the size of the region of interest, L, and the length of the test, nt. These are applied to set a practical minimum and maximum value to our hyperparameters. With this setup complete, we move to a simulated two-dimensional experiment to test the relative performance of the kernel functions and constraints. In the simulation, a spatiotemporal field was created with an oscillating radial basis function. The contour plot on the right shows the state of that field at 4 different times. A mobile robot was also simulated with a kinematic unicycle model to move in a circle. This is superimposed on the contour plot, and the dot shows the current location of the robot. Measurements were also made at each time step along the way, with zero mean normally distributed noise added along from the truth. The vehicle is set to drive around the simulated space in a circle for 60 seconds while making these measurements. Afterwards, the Gaussian process regression workflow and optimization is performed in order to generate the spatiotemporal map. 4 kernel combinations were selected and compared using this simulation. The first and second tests compared the radial basis function with and without constraints. This lets us see how the constraints affect the mapping performance. The third and fourth tests introduce periodic kernels through addition and multiplication. As there is no prescription for how to combine kernels, both were tested to see if there would be any variations in their performance. To quantify the results, a root mean square error was used to compare the relative performance of the 4 tests, as shown in the table. By comparing tests 1 and 2, we can see that adding constraints was an effective way to reduce the RMSE and improve mapping accuracy. Comparison of tests 2, 3, and 4 show that the squared exponential kernel and the additive periodic kernel performed best. In addition, the columns of the table show 4 spatiotemporal field periods that were tested by adjusting the oscillation rate of the radial basis function. The speed of the spatiotemporal field clearly plays a role in the mapping accuracy and capability. Looking at the full recreations of the spatiotemporal field in the figure, there's good alignment between the ground truth at the top and the mapping at the bottom. The overall shape is captured with highest accuracy along the path of the robot, as we might expect. To conclude, in this research, we discussed an opportunity for improved autonomous control in dynamic natural environments if a spatiotemporal disturbance map were available. To achieve this goal and overcome the sparsity of data collected by a mobile robot, we proposed using Gaussian Process Regression as our mapping technique. Both squared exponential and periodic kernels were considered, and physically derived constraints were imposed and tested and found to improve model accuracy. Ultimately, using squared exponential or additive periodic kernels gave the best performance. However, all kernel combinations lost accuracy as the spatiotemporal field period decreased. We anticipate further investigation into robot sampling and phenomenon speed to see how these factors affect the GPR spatiotemporal mapping performance. Now, to take this research into the real world, we are charting a course for field testing with an Otter uncrewed surface vessel on the coast of Lake Ontario. This snippet of footage from our USV during preliminary trials shows just how rough the coastal waves are for a small boat. So we're excited to see how our techniques can be applied and if there is any room for controlled performance gains. To wrap up, we'd like to acknowledge the support of the Ingenuity Labs, the NSERC Canadian Robotics Network, and the Vanier Canada Graduate Scholarships for their support in this research and in our ongoing work. Thank you.